We have an inverter, 12 volts DC input, 220 volts AC output, pure sinus wave, rated 4000 watts, which is clearly an overstatement. The two short leads are decently thick, and the crocodiles will rapidly hook up to the car battery. The instruction manual contains detailed information about the principles, operations and connections, and the parameters chart. Very good quality cable binders. Even though the manual specifies 12, 24 or 48 volts input, this particular model takes only 12 volts DC. I'm going to connect this 18 ampere hour battery. I've also added a voltmeter to check permanently the battery voltage. But voila, the inverter also displays input voltage. This was disappointing. I was hoping it showed the output voltage. The parameters I want to analyze are the stability of the output in relations with the input, the pure sinusoidal wave, and how much power can I extract. I put the outlet with the power meter, and I can see the power, current and voltage. I also connected a primitive oscilloscope. The load is a heater with 3 power settings. So no load, 12.4 volts input, 220 volts output, and the sine wave is pretty decent, no worries, not at all. So far it all looks very good. Turn on the load, first notch, fan only, 12 watts, all okay, the sine wave has no changes. Second notch, heater on, the sine wave is a bit deformed, but nothing to be worried about. I have 185 volts AC for 10 volts DC and 630 watts. This is good and bad. Good because 630 watts output is produced with relative ease and the inverter does not heat. Bad because the out voltage is heavily dependent on the input voltage. A bit of regulation would have been nice. So once again, let's test the load with the input and the output clearly visible. At higher load, my battery voltage drops significantly, but this is no wonder. For 630 watts at 220 volts is 2.86 amperes, but at 12 volts we need 52.5 amperes. This is ridiculously enormous. We are going to measure now the voltage of input and the current drawn from the battery combined with various output power. Right now the battery is 13.15 volts, almost 100 milliamperes drawn by this device when powered off. We're going to power it on. Almost an ampere drawn without any output. We have 2.5 amperes current drawn from the battery and 12 watts power output from this fan only. If I step up the power to 660 watts, we're going to have 73 amperes drawn from the battery, and the battery is 11.42 volts at 640 watts power. There is no joke with this kind of amperes. So 2000 continuous rating for this product is shameless exaggeration. This would require almost 200 amperes DC from the battery, and to carry this kind of current you would need wires as thick as a railway track. Not saying it can't be done. Of course it can, but this device seems too small for such big currents. So the pros and cons. Pros. The voltage is pretty stable at low loads. Only tested at 630 watts can take this load with ease. It has over and under voltage protection. The sine wave is good and stable with load. The fan for cooling kicks in only when needed. The overall build and accessories are good quality. The cons are relatively few, and the main complaint is the out AC voltage is heavily dependent on the input DC voltage. I would have preferred it to display the out voltage instead of the battery input. Though not tested, I don't believe it can handle 2000 watts continuously, or maybe for a very short period of time.
This is a solar charge controller. It charges the battery with a solar panel, and this is where you connect the solar panel, the battery, and the load, 12 volts load. The cheapest construction possible, self-tapping screws with plastic threads. And voila! We have a USB for charging the phones. As you can see, the negative is common for all the ports and only the positive is isolated. Those two MOSFETs connect the solar panel input with the battery. There is room for another two MOSFETs, theoretically doubling the load taken by this device. The only thing connecting the battery with the load supply is this diode over here. Let's put some voltage in it and see how it performs. Those MOSFETs use the backplate of this device as the heat sinks. I've made this installation. This is a power supply, the solar charger controller. This is the battery circuit, no battery so far. Okay, and this is the load. A bit of a heating element taken from a hair dryer. Alright, let's power this thing up and see what happened. Basically, this power supply simulates the solar panel. The solar panel is supplying this controller, but it doesn't start. So far we know it doesn't start with the solar panel alone. Let's hook the battery. I don't know what happens, but it is smoking. What the hell? It is not hot, but something is smoking inside. Anyways, doesn't matter, because we are supplying 14 volts from the solar charger. It shows 13.8 on the battery, and on the load, what the hell, nothing. Nothing on the load. Yeah, so this is where the smoke was coming from. This baby is toasted. Even though I have here 13 volts, 13.9, the output is gone. But the battery voltage, yeah, 14 volts. Let me see what happens if I turn on the voltage on the solar panel. 15, 16, 18, 19. The display shows 14.4 volts, which is not bad, but let's see what the reality is. 14.6. Not bad. In order to test the USB output, I have this USB testing device from AliExpress. 5 volts, 0 amperes, bang on. That's great. And let's plug in this studio light and see how it handles the current. So far so good. Let's turn on this light. 4.9 volts. This thing is good. It's taking in the load. Almost 1 ampere. It's very good. No worries. If I lower the intensity, I lower the current, and the voltage is perfectly regulated. Great. Let's see what happened if I disconnect the battery while it is working. Bam! Battery disconnected. No alarm whatsoever, so it doesn't detect the missing battery. Let's see the voltage on the battery output. 17 volts, 17.6 volts, not 14 as written on this LCD, but not 23 as written on the power supply. And this is what happened. The terminal just vanished. They should have gone this far, but they're absolutely gone. That's what happened. Perhaps if I solder them back it will work. This is not a diode, I was wrong, this is a transistor. The load was somehow regulated through this transistor, but anyway, I didn't like to half-ass these things, so I soldered back this damn transistor, and let's see if now it is able to regulate the output. I powered the board directly with this power supply instead of the battery, so I can change the voltage and see if the output is still regulated. So right now I'm feeding 15 volts through the battery, and let's see if I have some load. Yeah, 15 volts load, 15 volts of load. So the load is by no means regulated. I still had to test it under load. So the load so far is this resistor, this heavy duty resistor, which has a 5.6 ohm resistance. And let's see how it behaves under this load. And I'm going to measure now the voltage. Yeah, 13.3 volts divided by 5 ohms, and I have a 3 amperes consumption. No worries. And this is not bad. It displays 13.4 volts on the screen, and the load has 12.9 volts. Let's crank the voltage up a little bit. 13.2, 14 volts input, 13.3 output. It has a bit of regulation depending on the load. I see. Nah, it doesn't warm up. I don't know what happened before with this transistor, but it's not warm, and I have 3 amperes. Not just 1 star, but just 2 stars of competence. This is another regulator, a simple regulator. Quite a nice built one. They claim the input can be anywhere between 8 and 36 volts, and the output is bang on 13.8 volts up to 8 amperes. Well, we'll see about this in a minute, and for that I'm going to use this bench power supply, which is capable to supply up to 9 amperes, and a home build dummy load for testing stereo devices, switchable between 8 and 4 ohms, but I intend to put it in parallel, so I'll have 4 and 2 ohms. It uses decent beef thick wires, and I'm going to measure if the negative is isolated. No, it is not. Okay, the setup, as I said, is very simple. The power supply is connected to the input of the regulator. The output is connected to this dummy load. Switch to a 4 ohms measured with this multimeter here, which I'm going to switch it to voltage. And this, another multimeter, will be set to amperes, and will measure the ampere flow. Okay, the setup is done, and I'm going to write down some measurements. It claims to be regulating from 8 volts to 36 volts. So at 8 volts we have 0 output and almost zero current consumption, and it basically shuts down at 8 volts. starting clipping, and we see here that it's struggling to keep 13.6 volts output. This is great, this is fantastic. So at 8 volts we have 13.6 at 3.2 amperes. This is fantastic. So this little fellow does his job awesome. 10 volts we have 13.5 at 3.1 amperes. (13.2). The output is actually dropping a little bit with the increase of the input. So this power supply is not able to go only up to 35 volts, and I'm going all the way up. That's it. I'm giving it 35 volts, 36 volts, and the output is 13.3 at 3 amperes. So it is absolutely stable. I didn't expect that. It is fantastic. How about the warmth? Nah. Room temperature. Not a little bit of warmth at 3 amperes draw. And I want to increase the load from 4 ohms to 2 ohms. So we are up to 6.5 amperes. The output is bang on 13.3 volts. So at 2 ohms output, 14 volts input, 13.3 at 6.3 amperes. The heat is negligible, and I'm going to ramp up a little bit to 20 volts. Let's see what's happening. Precisely 6.3 amperes draw and 13.2 volt output. Let's go up to 30 volts. Let's see what's happening. At 30 volts for 6 amperes draw we have 13.3, so it's absolutely stable. It's rock solid. That's fantastic. I wouldn't expect that from a Chinese device. Such a stability. Awesome. Not a little bit of heat, not a drop. Great. So the results are great. This is a really awesome device. To come to work to test another feature of this device, and this is how my colleagues leave the workbench. Yeah, awesome. I want to test what happens if I exceed 8 amperes consumption on the output. So I use this power supply able to deliver 10 amperes. I set it to 15.2 volts, and we are currently taking 3.5 amperes through this huge dummy load I have here. Yeah, I just want to show you that the negative is isolated from the housing. So the housing, the negative, it's isolated. Now we are talking. So I have this device, this multimeter, which is set to amperes with a 10 ampere fuse. I better not blow the fuse. So we have 0.8, 0.9 amperes right now and 13.8 volt output. And if I'm increasing the load a little bit, we're going to 1 ampere. I'm curious just where the voltage is going to drop. We are drawing now 8 amperes according to the specifications, and we still have 13 volts. Nah, and we suddenly have 2 volts output. So this device actually severely limits the output when the current goes beyond 8 amperes. It's not just a sort of limiting and slowly dropping the voltage, it just cuts the output beyond 8 amperes. Okay, good to know. It's not just a limited output, but a switched off output. So this device is not a normal voltage regulator, but it's a real battery charger for a car alternator. It requires a battery to be connected to plus and minus for it to work, and it will charge and regulate your battery. So a nice device for battery charger for car alternator, not to be used as a normal voltage regulator. Okay, so right now I'm using this auto transformer made more than 50 years ago on the socialist era. Perhaps you can see here the famous logo. Nice. This auto transformer is adjustable, and I'm going to use it to power this 24 volts transformer taken out of an old UPS. Yeah, so after a lot of fiddling with the wires and everything else, I have my device connected to alternative. So I'm testing this device with the AC 14 volt maximum and see how it performs under a 4 ohms load. Switching now to volts. Okay, now so the auto transformer is connected. I only have 4 millivolts. Nah. From the AC point of view, I have 11 volts input, and from the DC point of view, no output. Okay, so the load is disconnected. It only serves as a support here, and the transformer is powered via the mains, and I only have minus 2.5 volts output. This is without the battery, but if I'm connecting the battery, I see that suddenly I have 13.5 volts. That's nice. That's nice. At only 11.6 volts input at AC. Let's see what happens if I increase the AC voltage via my auto transformer here. Okay. And I have AC 15.6 volts AC input. Alright, let's see what happens to the output. We basically have nothing on the output except for minus 2.6 volts, but if I connect the battery, I see that in DC, I suddenly have 15.5 volts. This is basically charging the battery. And if I'm connecting this ampere meter, I hope you can see it. Yeah, you will see that it's charging with starting from 2 amperes and it's dropping to 1 ampere and 0.8 amperes. So it's really charging the battery at 15.5 volts. So for 15 volts input AC, I have 15 volts output DC, and up to 2 amperes charging a battery. But the battery is charged, so that's not relevant. This is good. I'm going to drop the AC voltage to around 11 volts, 11.3 volts. In DC, I have nothing without the battery, but with the battery I have 13.5 volts. Let's see if this 13.5 is actually the battery voltage. Yeah, the battery voltage. Okay, what I found now around the house is another transformer, a puny transformer of only 18 volts output, and it's connected to our regulator, and with the help of the auto transformer we're going to regulate the input of the device and see what the output looks like. For an AC voltage of 12.4 volts we have a 13.9 volts, so the battery is charging right now. At 12.3 volts AC, the battery is charging. If I'm lowering the AC, the voltage is going down, and this is where it stabilizes. So this is, the battery is not charging right now for 11.5 volts. So it's starting charging from AC 11.5 volts, which is not bad at all. And if I go up to 18 volts, it is charging to almost 1 ampere, 0.81, and with 15.3 volts. That's good. And I would not use it for a mains powered car charger, battery charger for emergencies, like this one here, for example. Those two are not compatible.